All right, we're going to now move into using the Fenchel Dual for optimization. And a representative problem, which we'll actually see is quite flexible, that we're going to be considering, and I'm going to be referring to as the primal, is this problem here of minimizing f of x plus g of ax. And this format is going to be pretty flexible. We'll be able to model a variety of different formulations of different types of problems. And the reason that we would look at the dual, the reason we would try to exploit any type of structure in a problem rather than just saying I'm going to take gradient and just do gradient descent or do subgradient method, is exactly that we think that there is some kind of structure that can be exploited. So all of this segment that we're talking about now is different from the early lectures in this series, in that we're outside of the pure black box model where all we know about our function is I give you x, you give me back a subgradient. And so the name of the game here is to try to exploit some special structure of the problem and to set up general framework that can allow us to think about this in a principled rather than completely ad hoc way. Obviously, the best way to exploit the structure of a problem is to have already solved that problem and written down the solution somewhere. But that is not a principled approach that will allow us to extend. Okay, so the beginning of this whole story is looking at this formulation, minimize f of x plus g of ax, and then rewriting this in the following way, the following simple way. Rewrite this as a constrained optimization problem, but one where the objective is decoupled. So minimize f of x plus g of y. And now, just subject to the constraint that this problem is equivalent to the original problem, and that constraint is exactly y is equal to ax. And we're going to see that the dual optimization problem to this is maximize minus the Fenchel dual of f evaluated at minus a transpose z. So this is a maximization over a new variable z, or the dual variable z, minus the Fenchel dual of our function g evaluated at z. So deriving this is straightforward. So let's have a look at how this works. It's just going to find our Fenchel dual inside of this definition of the primal, and the key thing that we're going to make use of is strong duality. We haven't talked about conditions under which strong duality holds. I'll briefly mention those, but that's really the only the important hammer that we need to make this work. So let's derive that dual. Again, let me write down the original, the primal problem, min f of x plus, I'll write it in the second form, the constrained form, subject to y is equal to ax, and then we're going to dualize this, the constraint. So what that means is I'm going to write this as a min-max problem. So this is certainly equivalent to the problem of minimize over x, maximize over z, z is unconstrained, f of x plus g of y plus z times ax minus y. So so far we haven't done anything to assert that these are equivalent, because so by convention here, the inner optimizer gets to go second. So what min-max means by convention is that the outer minimizer has to commit to an x. Then the inner maximizer has all the power. Z gets to look at what x was committed to. X can no longer change from that, and then choose the worst possible z. And so, just based on that convention, you can immediately see that these things are equivalent, because the minimizer in that case won't dare violate this constraint, because if any of the coefficients of this constraint are violated in any direction, then this maximizer inside can infinitely punish you and make the cost plus infinity. So you don't do that. You choose an x and a y, so that y equals ax. But then if you do that, the inner max goes away. You've satisfied this inequality here, and the inner max goes away, and you're exactly left with the original problem. So these are equivalent. Okay, now by strong duality, which I've written down here. So strong duality is basically saying that min-max is equal to max-min. And there is a very commonly used sufficient condition for strong duality. So strong duality for a general convex optimization problem does not always hold, and there are not succinct conditions for when it holds. There are various sets of sufficient conditions. Excellent work on this is by Bertsikas, Ozdaglar, and Nedic. There's a book called Convex Optimization, Convex Analysis and Optimization, which talks extensively about strong duality and arguments of how we can derive it from different sets of sufficient conditions. But for us, it's going to be enough to just just assert that this is true. And I'll just write down, one of the most common sufficient conditions is Slater's. And Slater's condition says that there exists some x hat, not the optimal x hat. Maybe I won't write x hat, I'll write x tilde, because I don't mean the optimal. That's an element that's in the interior of the domain of F, and so that a x tilde is in the interior of the domain of G. So those are the properties that we need. But if that's true, then going back up top, this is equal to maximization over z, minimization over x, of now a problem. If we look at the inner minimization problem, it now no longer has any constraints. So this is equal to f of x. Oh, I'm sorry. This of course should have been x comma y the whole time. Right? F of x plus g of y plus z transpose ax minus z transpose y, and now there's no coupling between x and y anymore. There's no constraint y equals ax, and so this inner minimization problem, which is going to be a function of z, because the min has now the luxury, being inside, of getting to see what z gets to do. So let's look at this. This minimization problem I can just write as it decouples, because x and y never appear in the same term. So x can do what x wants, y can do what y wants, and they don't have to discuss. So I have minimize over x of, let me write this slightly differently just to make it a little more suggestive. A transpose z transpose times x. So you see that this is exactly this term here. Plus f of x, and then plus min over y of minus z transpose y plus g of y. And you see that this is beginning to look like a Fenchel transform. It doesn't look like it exactly. First of all, Fenchel transform is defined using a soup. Here I have a min, so I need to change that. But these are all things that are that we can do. So I'm going to just force this into the form of the Fenchel transform, and we'll do this term by term. And this is all straightforward. So this is equal to minus the soup over x. And then now I need to put a minus inside, minus A transpose Z transpose x minus f of x. And then again, minus the supremum over y. I need to put a minus inside, Z transpose y minus G of y. And indeed, this is now exactly the form that I want. So this is exactly f star evaluated at where? Evaluated at the point that is multiplying x. That's minus A transpose Z. I have this minus sign outside, so I'll write that later. And what is this? This is exactly G star of Z. So that means that overall, this is equal to, this inner min is equal to minus f star of AZ minus G star of Z. So therefore, the dual problem reads max. And now the min inside, we've already processed the min, and we're left with minus f star of minus A transpose Z minus G star of Z. And this is exactly what we had on the previous slide. This is what we wanted to show. So this is what we're going to be working with. So this is the whole story, that we could have something like this. That's fine. You use all of the algorithms that we've developed in the primal, or we can now take the dual and try to work in the dual. And let's examine what this dual, what are some of the properties or some of the first properties of this dual. This is a maximization of minus convex minus convex. So equivalently, note that I could just bring out the minus sign one more time and just have a minimization of convex functions. The point is that this is maximization of concave or minimization of convex. This is a convex problem because f star and g star, as we've established, are themselves convex problems. So what is the story going to be going forward? It's basically going to be saying, I started out with something convex, now I have something convex. So when is it advantageous to go through the computational effort, which can be substantial, of going into the dual and then working in the dual, as opposed to just staying in the primal. So this is basically the outline of our story. Nothing, there's no, this as I mentioned, this whole segment is about exploiting special structure. So just taking the dual is not a generic way to make a problem easy. And that should be expected, since duality is not doing anything. And we know the dual of the dual is the primal, so there's nothing magical about taking the dual unless there is some very special structure that's being exploited. So this is basically what we're going to learn to look for and try to learn to exploit going forward. So let's start with the very first thought, which is what are optimality conditions look like when in the primal and in the dual. And this is going to also bring back this concept of the Lagrangian. So our original problem is minimize f of x plus g of ax. And I know that x hat, which alternately I write as the constrained version, min f of x plus g of y subject to y is equal to ax. And we know that x hat is optimal. It's an unoptimal solution if 0 is an element. We've written this is the same thing we've written down hundreds of times. The subdifferential of f at x hat plus the subdifferential of g of ax, I need to use the chain rule, plus A transpose times the subdifferential of G at A x hat. So what does this mean? This means, i.e., x hat is optimal if there exists some z that's an element of the subdifferential of G at Ax hat that satisfies minus A transpose Z is an element of the subdifferential of F at X hat. I'm just rewriting these relationships. I haven't done anything really of consequence. So this is what it means, existence of Z. And of course I wrote down Z because we're now thinking of elements in the subdifferential as dual variables. So again, thinking back to the relationship between the subdifferential of a function and the subdifferential of its Fenchel transform, we know that that elements of the subdifferential are really going to be our dual variables. And this is used a lot in convex optimization. In particular, it's elements of the dual that are a proof of optimality of a particular point in the primal. We haven't really phrased this that much, except the main time that we really use this substantially so far is in our lectures on proximal gradient and showing that the proximal mapping is when we explore the properties of the proximal mapping and showing that even though it's not an element of the subdifferential itself, that it's equal to zero only at the optimal solution. But more broadly, this concept that elements of the subdifferential are proofs of optimality of certain points. Again, it's very simple. This is one of the first things we did when we were talking about optimality conditions. But this is something that is used a lot in convex analysis and convex optimization. And it's important to get used to thinking about that, especially, and it's emphasized even more by looking at optimization in the dual, because exactly now elements of the subdifferential are essentially variables of our dual problem. But what we're really doing is, instead of optimizing over x, we're trying to now look for a subdifferential, a subgradient that proves that a particular x is optimal. That's one way to think about what the dual is doing. And it's especially clear, this kind of picture is crystal clear if you, take what we've said now and think about linear programming. Think exactly about what is this whole story in the linear programming setting. What do dual variables look like, and what is their relationship to subdifferentials, etc.? So I invite you to do that, and I think it may allow you to think a bit more deeply about this, and I hope clarify what the connections, what some of the connections are. Okay, but back to where we are. So this is optimality conditions, and what this is equivalent to. This is equivalent to saying that we have x hat and y hat equal to ax hat that are minimizers of the Lagrangian function, which I'll define now. So the Lagrangian is a function of the primal variables and the dual variables. So xy, my primal variables, and z, and it's just equal to f of x plus g of y plus z transpose ax minus y. And for any z, we need, so x hat, y hat optimal for a given z. This means that 0 is an element of the subdifferential of f at x hat plus z transpose A, and 0 is an element of the subdifferential of g of y minus z, which is another way of saying this. So the optimality conditions are exactly the optimality conditions of the Lagrangian. So let's use the rest of our time to look at some specific examples of how we use this framework. So let's look at a problem of minimizing a function subject to some set constraint. Min f of x subject to ax minus b belongs to c. Now I could have just written x in x, but what I did is I wrote an affine transformation of x belongs to some other set c, just to give it a little bit, just to give it some structure that will be that we're going to exploit. Actually, I'm not giving any structure. It's both versions are completely equivalent in general. What I'm really trying to say is that writing it as x minus b is an element of c is one step closer to many different types of problems that we're going to see. But otherwise, this is a completely general constrained optimization problem. As we did even in the very first. When we're just learning about subgradient method, we can just write this as minimize f of x plus an indicator function of the set C of ax minus b. And now you can see that except for this minus b part, this is looking a lot like f of x plus g of ax. In fact, g of ax could, g of z, it could just be the indicator function of z minus b for the set C. And then now we're exactly in the same form that we had before. So I can write down the dual. So if this is g of ax, then writing out the dual and using the calculus rules that we had seen when we were first introducing the Fenchel Dual, which tells us that translation, the impact of translation, you can check that, and I hope that you will do these calculations, even though they're repetitive. That's somehow the point, just so that this isn't, it doesn't appear like magical at every time, and we gain some intuition of, okay, what is this dual? What is the dual going to look like? So we know the dual is going to look like minus f star of minus a transpose z minus g star of z. And what's g star of z going to be when g is equal to when g is equal to the indicator function of a set C? So this will be equal to minus b transpose z. This is that shift that I mentioned, minus the dual of the indicator function minus f star of minus a transpose z. And now we can look at what happens when we have different, very common settings. So let's specialize this to different settings. So I guess sub-examples. The first one we think about is minimizing f of x subject to an affine constraint. So what happens there? So let's see what these pieces are when we have that. So sub-examples are minimize f of x subject to ax equals b. What happens? So our set C here is what? I need ax minus b to belong to the set C, so C is just a zero vector. And that means that the dual, I need to write down what is the Fenchel transform of the indicator function of just the point 0. And again, you should just check that this thing is just 0. Another example is if I have minimize f of x subject to x being in an affine transformation of a ball, or in other words, an ellipse. Or rather, I shouldn't say an ellipse, but a norm, an affine transformation of a norm ball. Subject to ax minus b bounded. Let's just say bounded by 1. Okay, so what is C in this case, and what does the dual look like? So I need to write that ax minus b belongs to C. How does that translate into norm of ax minus b less than 1? That's just saying that ax minus b is in the unit norm ball for whatever norm we have. So that means that C in this example is just equal to the ball with respect to whatever norm we're talking about of radius 1. And we actually derived this in one of the earlier lectures on Fenchel duality. The Fenchel dual of the indicator function of a norm ball is exactly equal to the dual norm. So this is equal to the dual norm of z. And then a third example is more general linear program or semi-definite program or some conic optimization problem. Minimize, I guess even more general because I'm not assuming linear objective. Minimize f of x subject to ax less than or equal to, and this notation means less than or equal to in the cone ordering. So in particular what this means is that b minus ax belongs to the cone. Think about semi-definite optimization. Think about optimizing subject to a positive Orthin constraint. So this means that b minus ax is greater than 0, where the greater than is really the cone ordering. So another way to write that is b minus ax belongs to the cone. So again, in this case, C is equal to minus cone, because it's saying that ax minus b is less than 0 in the cone ordering, which means it belongs to the minus cone. And the indicator function of C, the dual of that, is in fact equal to the indicator function of the polar cone at Z. So again, please check all of these. Please check these for yourselves, and also just make sure you take it to the end. So write down, okay, what is the dual problem when I have minimize f of x subject to ax equals b, or what is the dual problem when I have this this cone constraint? Okay, let's look at another very common problem. Now I no longer have a norm constraint. I have the norm up in the objective. Minimize f of x plus some norm of ax minus b. And this is exactly in the form, this is already in the form of minimize f of x plus g of ax. And here g of y is just equal to y minus b, the norm of that in whatever is the norm that we have. Okay, so we know the dual. It's maximize minus f star of minus a transpose z minus g star of z. So we need to compute what g star of z is. G star, what is that? So again, we have translation, and so we know how that's going to look like. So recall again, I'll just write this out, but we used it on the previous slide as well, that if I have a function h and I'm looking at h of x minus b and I'm looking at the dual of that, this is equal to b transpose is equal to, I guess I need to evaluate this somewhere. The dual of this evaluated at z is b transpose z plus h star of z. So this is what we've been using. This is what we're going to use here, and we're also going to use the fact that, again, what we used on the similar previous page is that if I have a norm, that's a function, so I can look at its Fenchel transform, and the Fenchel transform of a norm is equal to the indicator function of the unit ball in that norm. I'll just denote it. I'm sorry, the unit ball in the dual norm. So this is what that is. So that means that g of z star, we can write this down. This is equal to b transpose z plus the indicator function of b in the dual norm evaluated at z. And we don't know anything about f, so we can't simplify this or try to do anything further. We're going to see a number of different examples, but that's it for this lecture, and we're going to continue to see how we can exploit further different properties of f and g.